Okay, good morning, everybody. So, we were discussing about rotameter, which is another obstruction type flow meter, which we call it the constant pressure drop, variable flow rate, variable area, uh, differential pressure sensor. Differential pressure type. So, first thing is that we have a vertical tube. It must be a vertical and the flow must be from the bottom to the top, and the tube should be a tapered one, opening up at the top, and there is a float. And as I told that as the flow rate increases, the float will go up like this, and we can have some calibration of the what is the in terms of flow rate, and just looking at the position of the float we can say that what is the flow rate. Of course it has to be calibrated, and the expression it was qv is equal to cd discharge coefficient, at area of the tube at that position, af area of the float, which I assume is constant, divided by square root of 1 minus at minus af by at square into square root of twice g by gamma 2. Gamma 2 is the density of the float into Vf, the volume of the float, Af, area of the float, and gamma 1 and gamma 2 basically, uh, gamma 2 is the A of the specific weight of the fluid, and gamma 1 is the specific weight of the float. This we have already discussed, and we have shown it that this will be is always constant at the equilibrium position. And if we say that if at minus af by at whole square is much smaller than 1, then we can say qv is proportional to at minus af, and if it is calibrated, so if I say this is y, then if at varies with y, in such that at is proportional to k1 plus k2y, in that case qv you can say that this is equal to, okay, proportional to, okay, I just put them dashed, is equal to k1 plus k2 into y. So what we said is that important is that linear scale. So that is the very important thing, and we need not do complicated operations like square rooting, measuring the differential pressure, so all the things there. But definitely this is less accurate compared to A, but it is easy to visualize the flow rate there. But few questions we had already mentioned, but possibly we didn't answer. That first question is that why it is called a rotameter? That is the first question. And second thing is that you say the accuracy is less. At the same time, we told that it could be used as a standard meter for calibration like this. What does it mean there? So, before that, if we are discussing that one, we must say that the sources of errors, what are the inaccuracies, are in fluid density. because the fluid may have, we are with water, but maybe there is some, it is used for brine, or some salt is being added to the water. The density will change, and as a result, the this will give you gamma different values. So there would be some error. Next is that due to viscosity, because we have already told uh, that viscosity, we are neglecting the effect of viscosity or effect of static, I mean the friction, we are neglecting that one. So naturally, if the viscosity, if the flow rate is low, but the viscosity is high and like this, so that effect will also be there, because it will be modifying the Bernoulli's equation. So there would be some correction factor also like this. But at the same time, we told that in compared to the other obstruction type flow meter like Venturi and Orifice, here we can measure flow rate more accurately if the flow rate is low. The flow rate is low, we told that that means while in other cases we had it, say suppose 4 is to 1 or like this, that is the minimum and maximum flow rates. For other cases, it was 4 is to 1 or something like this. And the minimum flow rate may be in the range of 10 is to 1. That means we can have a very low flow rate there. Then definitely the question is that if it is low flow rate, so can't viscosity affect the performance? That is another issue. So then only we can say if these two sources of errors, we can take care that it should be insensitive to the density of the fluid, or also we make it insensitive to the viscosity. The viscosity also, definitely you can have it a better performance in the sense that it can be used as a wide range of flow like this, and that's why we call it a standard instrument for calibration. It could be used because we say that it is not affected by the variation of the fluid density as well as the variation of the viscosity. So, what are the tricks? Why, how can we make it like this there? So, for that one, we need to go to the construction of the float, because float design is a critical one. I wanted to say that by carefully designing, by intelligently designing the float here there, we can make it in both the things there, insensitive to the flow rate, I mean the fluid density, and second thing is that insensitive to the viscosity effect there. So the design of the float. So if we want to design the float, first of all we need to see, ensure that number one is that float must be held vertical, so that it does not touch any of the side or gets inclined and like this. So first float must be held vertical, and that is possible if we design the float such that its density is near, I mean rather the center of gravity is towards the lower side of the float. And second thing is that what we want, that should create uniform turbulence to make it insensitive to viscosity. What we wanted to say, that apart from that, even if that here the viscosity is high, the Reynolds number is low, the float, at that time of float, it passes to the float, we should make such a there such that there is some extra turbulence in it, so that the Reynolds number, there is some extra turbulence in it, so that there would be some Reynolds number will be high and the effect of the viscosity will be neglected, can be neglected. So, we are adding some more extra turbulence by the float, by the designing the float, so that the effect of low viscosity can be neglected. What is the way? That is the thing possibly you can now understand that why the name comes. We can create some turbulence, additional turbulence, if you make the float rotate. If you make the float rotate. So, if it is rotating, then there would be some additional turbulence in it. So, naturally, there would be more, the viscosity effect will be less. So, the construction is important, and how do you do it? And possibly, now you can understand why it is called rotameter, because whatever is the float, it rotates, and we make the design of the float such that it rotates, and that's why the float rotates, that's why we call it rotameter there. So, what is the construction? How does it? Can we make the float rotating? That is done by this way. Okay. So, first of all, this is held in this shape, so that the CG comes below, so that it becomes vertical. Apart from that, what is there, they do it. These are called angular groups. That means some small channels are being made in the flow like this there. So, that is, and these are all angular in shape. So, if there are certain small channels in it, then what will happen? The water or the liquid will pass through it, because there is an extra liquid, there is a small gap there is a small channel there, this will pass through it. And since it is always angular, then what will happen is that as a result, there would be some rotational torque developed, because if once it passes through it, they will always give a force to this float, and that will try to rotate it like this. So, as a result, what will happen, that this float will rotate, and this will rotate, and as a result there is always some rotation of it, and that creates basically the flow is coming to this end, and like this on those ends basically the fluid, there is some additional turbulence is being created, and that makes the flow to be more turbulent, and as a result the viscosity will be, effect of viscosity can be neglected there. So, this is a important thing here. Reading insensitive to fluid density. So basically, we need to make the fluid it is the reading insensitive to fluid density. So naturally, in that case, we will have to be the what is the density of the fluid float we should choose. That means what is the material we want to choose, and we will have to choose so that it is insensitive to the fluid flow. If we recall once again the expression QV is equal to some constant into 2G by gamma into Vf by Af into gamma minus gamma 2. It is gamma minus gamma 2, and this is, we call it a volumetric flow rate. So, we can see that gamma 2 is the fluid density. If the, sorry, 2G by gamma 2 it would be, is the fluid density. So, what we can do is that, basically we can say this is equal to K root over 2 by rho, we know. This is Vf by Af into gamma 1 minus gamma 2. So, what we can say that if gamma 1 is much small greater than gamma 2, that means this float material density is higher, much higher than the water or the, if it is air, it is obvious for water or like this, so that it is heavier, then we can say that QV is independent of a fluid density. Apart from that also, because sometimes it is expressed, it is, we called it a volumetric flow rate, but sometimes it is desired to have the output or the reading in terms of what we call it a mass flow rate. So, the mass flow rate is nothing but m is equal to the volumetric into the mass, it would be gamma 2 there. So, what we can have it, so this is equal to, say, we can say this is K into what we say 2 by rho Vf, okay, this will be rho 2. I can put it like this. There are 2 by 2G by gamma 2, I put it like this again, put back to gamma 2 there. So, we can see that this will be, other things are constant, I can take it out outside, I call it K1, or rather K here and the K1 inside, I can say it. But once you multiply with gamma 2, then it comes to be is equal to, this will be gamma 2 square inside this one. It will be gamma 1 minus gamma 2 into gamma 2. Okay. So, what we need to do is that dm d gamma 2 should be equal to 0, so that it is not, the mass flow rate is not dependent on the value of gamma 2 there. Then for that case, what will be the, if we differentiate it, what will be the result? The result will be, you just differentiate it, it is gamma 1 minus 2 gamma 2 equal to 0. And if we make it gamma 1 is equal to 2 gamma 2, that means around this, if the float density is around approximately twice the gamma, I mean the fluid density or fluid specific weight, then we can make it nicely, and independent of the mass flow rate is independent of the fluid density. So, it is important. So, if it is a fluid volumetric flow rate, we try to make the float heavy, and if it is mass flow rate, we try to make the flow density should be double to that one. Obviously, that may be very difficult to design unlike this, but often what is done to achieve that one, the float is made of hollow material, so that you can you make float hollow, so that improperly designing the thickness and like this, you can make the gamma 1 is approximately equal to gamma 2. So, this is an interesting there. So, sometimes we use metal float, or if we use plastic sometimes where we require double the density or like this. So, these are the things we have.
Hello, sir.
Yes.
So when like gamma 1 is very large, then gamma 2, then how QV is independent of gamma 2? Like there will be this
This one.
denominator, like, yes,
This
sir.
one. So, if gamma 1 is less than gamma 2, that means if gamma 2 changes, QV will not change much.
Sir, but like in denominator also gamma 2 is present. So how are
No,
we?
you see the denominator, that's why I wanted to avoid that one. You know what is gamma 2 is equal to rho 2 into G. So, it is rho 2. Gamma, you know, is equal to rho into G. Okay. So, no gamma there, it is rho 2. Hmm. Oh, you mean to say that even if you make the gamma 2 A there, but you know at the same time, so you are telling that in the denominator also rho 2 is varying there. Yeah, I agree with your point, but you see gamma 2, how much it changes, 5%, 10% or like this there. So, in this case, what we make it, this gamma 1 is very large, and if it is very large, we can, obviously I cannot make it del q del gamma 2 equal to 0 in that way, but definitely it would be less dependent. That much I can say. Okay. Please go
Okay,
through
sir.
Bentley's book or other books. These are more detailed designs and particularly mechanical measurement books. They have got more detailed design of this one. So we must have come and understood that rotameter, though it is a small instrument, but it is a very interesting one in that way that it is also a bridge between control and instrumentation, as we told about the history and about that one also. So you can look into that point also. Okay. So we stop here. So always we will find any plant or like this for visualization, there is a rotameter connected to it there. Okay. But it must be held vertical and the float has to be designed properly. Now we go for the next topic, because as I told that the flow meter at maximum number of flow meters are there depending upon, because flow measurement is a very important one. We require the flow measurement in different situation. It may be the flow rate of a river, how much, what is the velocity of A there, water it is moving in an open channel or like this. Those are the things there. But apart from that, there are other cases also there. What is on, we call it, next one I will discuss about turbine type flow meter. Obviously, this is all known, principle is known. Whenever you must have tried in your childhood or like this, whenever there is a flow in a channel or like this, if you put some fan or like this and place the fins properly, then this fan starts rotating. And by measuring the speed, you can know, we can estimate what is the flow rate. So that is what is called a turbine type flow meter. Primarily, it is like this. So what we do is that this is the front view of it. There is a what we call it a turbine. So as the flow change passes through it, the turbine should rotate. But for that one, the blades of the turbines must be angular. So we can say that, yes, what is the construction? Say suppose the fluid is moving in this direction. So what we have, we have several blades like this here. But these two I am showing it, they cannot, the angular A is not visible here, but actually they are inclined, each blade is inclined by an angle alpha there. So what will happen? Because of the inclination, the turbine will rotate and we can measure the speed also there. So suppose I call the diameter of the turbine is D, the whole pipeline, and the hub, the diameter is small d, and say this is your velocity V, and I can draw this way that this is your velocity and it is rotating. So there is always some angular velocity. It is omega is the angular velocity. And what we call it basically, this is omega into r divide, and this is the velocity v. And if we can say that r is the radius of the blade, because this radius, what is the radius of the blade, we can find out. So we can write it down that omega r by v is equal to tan alpha, because they will constitute an angle. This is the alpha, which is the blade angle. Alpha is the blade angle. So we can say that omega r divided by q by a is equal to tan alpha, or the constant is equal to omega by q, that is a linearly proportional This is equal to tan alpha divided by R into A. And what is A? A is the effective flow area. What is effective flow area? It is pi by 4 into capital D square minus pi by 4 into small d square. But we need to consider the area of the blades also. Say each blade has got a thickness T, we can say it. So what we can say is equal to minus of m into r minus d by 2, small d by 2 into thickness. What is the m? M is the number of blades. So we can say that if this is m number of blades, each gun we can say of this one considered as a rectangle. And so what is the area? That is basically r minus d by 2 there. So all the things known, definitely we can calibrate it, the turbine type flow meter here there. So we need to measure the speed of rotation. Can you suggest a technique that how can you measure the speed of rotation? Yes? How you do measure the speed of rotation? Anybody?
So
What up? Yes?
maybe some sort of LVDT can be used. I don't know. I'm just guessing.
LVDT. LVDT, where do you connect? So first of
So
all, anything you cannot, it is all inside. You cannot connect anything LVDT A with the blade because then it is rotating at a high
sir,
speed.
yes, sir. Sir, because it is rotating, obviously it can't be directly connected. So maybe some gear, using some gear, we can transfer it to linear motion and then check it.
Try to have a simpler one. Try to,
So that capacitive rotating plate type of sensor which we discussed, in
yeah,
which
difficult.
square wave
And
currents will.
think of inductive capacities more than that. Anything? Very
So we can
simple.
use motor,
Yes?
motor. Like we'll
Motor.
connect.
No, no, motor, it is rotating. So how can you, I mean, you mean to say tacho generator. How can you connect a tacho generator? So the measurement methods, you can have it, how do you measure the speed of rotation? So the question comes that, okay, if we have some rotating body and in this case, blades are also there, how would you measure the rotational speed there? So that can be used by an one is optical detection. What is there? What you can do is that you can have a blade there and we can have a optical source and a optical detector there. Okay. So what we are doing is that we are trying to put some light using some LED or like this there. So maybe an LED, it is a, and it is a photo detector like this there. So you put some light here and the light will be reflected back if the blade is there, and if the blade is not there, there would not be any reflection and it will pass through it. Then what will we get? In the detector output, we will get it simply some sort of square wave, okay, and you measure the number of pulses you receive per minute or per second, and you get the speed of rotation. Got my point? So this is one way of it, like this. Or otherwise also you can put, this is one. Another way, you see, we call it a magnetic detection. Sometimes we put some, we can do it on every teeth. I put a small magnet. Okay, maybe the North Pole is here and the South Pole is here, or we just put it like this here. Okay, and we use some sort of search coil. That means whenever it passes through this one, uh, there is a change in magnet. Whenever this blade comes in contact with this one, there is a change in here there, and definitely what is there? Magnetic field there. Obviously, there would be some excitation coil also. I don't have space. That's why we can do it. So there would be a change in flux, and the change in flux, wherever, how many times this change in flux, or this, and definitely some voltage is induced. So the frequency of the voltage induced, you can do the things there. Or sometimes we use, obviously this one, a Hall effect sensor. Hall effect sensor, what it is? You know possibly that Hall sensor, they are also, because all the things I cannot discuss in the class, but you must look into it, that Hall sensors are basically, if we go for it like this, say suppose there is a material, Hall material there. What we do is that we pass some current, constant current through it. We pass some magnetic field perpendicular to this one with, then in that case there would be some voltage induced E1, E2. So the voltage induced E0 is equal to E1 minus E2, basically this potential there. And this is equal to some K into B into I there. So B is the flux density there. So definitely whenever the magnet passes, instead of this search coil, I put a Hall sensor there. Very tiny Hall sensors are also available there. So we can put Hall sensor here. So whenever the magnetic pole comes in vicinity, the flux density changes, and as a result there would be some voltage induced, change in the voltage, and we measure the how many times you get, how many times you receive the pulses, and divided by number of blades, you get the speed of rotation. Okay? So that is the way we can go for the turbine type flow meter. Is it clear? So there are many, of course, optical methods, optical technique would be discussed more in detail afterwards, uh, and maybe in the second day. But this you can easily, the photo detector and LED, you must have done some experiments also in your higher secondary level, also like this. Then, and you, those if you are crazy, you must have done some experiment at your house itself there. Okay. Next is that positive displacement flow meter. This is basically what we call it integrating type. As we have mentioned earlier, that wattmeter is an indicating instrument. It measures instantaneous power. But energy meter is an integrating instrument that measures the total power consumed or like this. Similarly, flow meters, this turbine type flow meter and all other things are indicating. So, at an instant, how much flow, volumetric flow or mass flow rate is going, but basically integrating type, if it is an integrating type, then we can have it, we call it a positive displacement flow meter. Obviously, you may say that this QV, if we integrate, you have some voltage, if we integrate it over time, you can get a volumetric flow rate. But definitely, this integration and like this, but it's more complicated. But we want to have a simpler type of instrument which can be used in petrol pump, in your house, to know that how much water you are consuming. So, this is very important and we often use, of course, there are many number of types, different types of mechanical designs are different, but basically it is a mechanical instrument, I will call it, because it is a mechanism, they make some mechanism and by which we can find out what is the flow rate. So, whenever you ask for, okay, give me a 5-liter petrol and to the petrol pump, so there is some machine involved which measures the exactly the quantity of what petrol flowing through that period, throughout the period that valve is open there. Let us see the simple constructions of it here. I am telling you there are a number of designs, but basically they are of this type. What is it? There is a peculiar type of what I will call it an unstable container, I would say it. It's an unstable container. Wherever, so at the center there is an inlet hole where the water or the fluid we want to pass it. So, it first goes to the upper chamber and then from once it overflows, it goes to the lower chamber. But as soon as it gets filled up and this lower chamber also comes to the certain level of water, what will happen? Its CG changes and it becomes unstable and there will be, as a result, this will be tilting. Once it tilts, what will happen? This water or the fluid here will come over the there, a reservoir or something where to the earth which is connected to the out channel. So, this will drain all the there, water inside there, and go to the outlet there. And again, once it drains it, it comes back to the original position. CG comes back to the original position, and as a result, it lifts up. So what will happen is that, so once the inlet is there, so every time it comes to a certain level, it tilts, it keeps some those liquid, drains some liquid to the outlet channel and goes, and again it is filled up, and again it goes on like. So basically, what we see that we measure number of tilting. Measure number of tilting, and that will give you the what we say, the total flow rate. So because maybe each one is a half liter, 1 liter containment. I mean, just I'm giving it, maybe basically much smaller, and once it tilts, it goes to that one, and number of tilts in per minute or per hour you can get it, and that will be your flow rate. And tilts you can measure, and you must have seen now, you can measure it any of the optical method or the magnetic method, and this way you can measure the tilt. So it's very interesting, but at the same time, the simple type of construction, which is call it a positive displacement flow meter, and that is basically to measure the total volumetric flow, which is a total amount of liquid you are using or consuming, water or petrol or like this, to get it. So I stop here. I think time is not further. So if any question, I can quickly go through it and we can answer. Is it okay?
Sir, I have a doubt, sir. So, if we have a continuous inlet, like if the input is continuous, so when it is tilting, still the water or whatever is coming will be coming, right? So, at that time also it will be filling up. So, I did not exactly understand.
You
Um,
might say that whenever it is tilting, then again the water will be coming. But
yes, sir.
definitely this container is much bigger, and it quickly tilts because of its mass and will quickly crunch back. So whatever the water comes in here, that would be there and it will be going for the next tilt.
Okay, sir. Okay, got it. Yeah.
Yeah. Any other question? Okay. So
Sir, so basically we are not using like what I initially thought was we can measure time, and then if it is a uniform flow then we can measure time and then accordingly. But if the flow is not uniform, in that case we will be using such kind of instrument.
yeah, but if we can do the integration in that way, whatever every time instant you measure the flow rate and total integration, give it to an integrator. That also do it, but it is more complicated, and we know flow measurement is always difficult. Like this here.
Yes, sir.
It
Yes, sir.
is
Got it.
much more small, simpler, and these things are going on for actually, as I told, in those days, you know, if we look at it, that in science and technology, definitely many countries contributed, but Italian in the beginning of this AD, few 50 AD or 100 AD or like this, they were good engineers. They made some uh, drains or canals or like this and provided to their different households and like this, and they had to control that, okay, what is the amount of flow, amount of every household should receive, the water it should receive, and that's why they had made this sort of often type of flow measuring devices and flow rate there. Obviously, I would say that in the Indus civilization also, there are systems of canals are like this, in the drains and where they used to go feed water to different households. But still now I have not found any technique for measurement of flow rate there. I don't know. Maybe there is, maybe some more there. But as I told, that the history of flow measurement is very much important, and it is going along with the development of science and technology. Okay. Thank you very much.
Thank
So
you, sir.
next day we will continue some more types of flow measurements.